Welcome to Chapter 5 Semiconductors. In this chapter, we will explore a fascinating category of materials that are neither perfect conductors nor complete insulators semiconductors. These materials, like silicon and germanium, are the heart of all modern electronic devices, from smartphones and computers to solar panels and sensors. We'll look into how their electrical conductivity can be precisely controlled through temperature, light, and doping, the introduction of small amounts of impurities. You will learn how semiconductors enable the operation of diodes, transistors, and integrated circuits, forming the foundation of digital technology. By the end of this chapter, you'll understand why semiconductors are often referred to as the brain of electronics. We're going to explore the incredible materials that sit right between conductors and insulators. These are the backbone of modern electronics. They make diodes, transistors, integrated circuits possible. What makes them special is their ability to control electrical conductivity in a very precise way. As we dive in, we will discover how semiconductors strike that fine balance between allowing and blocking electrical current. This property is what allows your phone, computer, or even a massive data center to function smoothly. By the end of this chapter, you'll understand how semiconductors drive innovation and shape the future of technology. Semiconductors are special materials they have conductivity levels between conductors, like copper, insulator, like rubber. Their conductivity falls within a broad range, between 10 to the power of negative 4 and 10 to the power of 4 ohm, inverse meter inverse. That's a wide scale, but it tells us one key thing. Semiconductors do not conduct as freely as metals, but they are also not completely resistant like insulators. This behavior is closely related to something called the band gap, the energy difference between the valence and conduction bands. For semiconductors, this gap is typically less than 2 electron volts. Let's take silicon for example. It's the most commonly used semiconductor, with a band gap of about 1.1 electron volts. Germanium has a smaller gap, around zero point 0.7, and gallium arsenide, a compact semiconductor, sits about 1.4 electron volts. So what does this mean in practice? The smaller the gap, the easier it is for electrons to jump and conduct electricity when energy is applied, making these materials perfect for electronics that needs controlled current flow. So let's talk about intrinsic semiconductors using pure silicon as our example. In a pure semiconductor, the number of conduction electrons is exactly equal to the number of electron holes. That means for every electron that gets enough energy to jump into the conduction band, it leaves behind a hole in the valence band. These materials, like pure silicon or germanium, don't have any impurities. That's why we call them intrinsic. Their electrical behavior is solely based on the structure and temperature of the material itself. Now we can express their conductivity with a simplified equation. Conductivity equals N times Q times the sum of the mobility of electrons and holes. In plain terms, N is the number of conduction electrons, Q is the charge of an electron, nu is how easily the electrons move, and nu h is how easily the holes move. The graph on the right shows us something important. As energy increases, more electrons make the jump on the conduction band, creating what's called an electron-hole pair. These pairs are the carriers of current in intrinsic semiconductors. As we raise the temperature, more of these pairs are formed, which increases conductivity. Let's calculate the conductivity of germanium at 200 degrees Celsius. We will begin with the basic conductivity equation, which says the conductivity equals the charge carrier density times the electron charge times the sum of electron and hole mobilities. Using the data from table, we are told the carrier density is 23 times 10 to the power of 18 per cubic meter. The electron charge is 0.16 times 10 to the power of negative 18 coulombs, and the sum of the mobilities is 0.364 plus 0.190, which gives us 2.04 Siemens per meter. Now we want to find the conductivity at 200 degrees Celsius, which is 473 Kelvin. To do that, we apply the temperature dependence of conductivity using the exponential equation that involves band gap energy. We are given the conductivity at 300 Kelvin, which is 7.11 times 10 to the power of 5 Siemens per meter. We substitute into the exponential formula with the band gap energy of 0.66 electron volts and Boltzmann constant. After calculating, we get the conductivity at 200 degrees Celsius as approximately 217 Siemens per meter. Intrinsic semiconductors are pure materials. That means they conduct electricity because of the properties of the material itself, without any added elements. But when we talk about extrinsic semiconductors, we are referring to semiconductors that have been intentionally modified by adding other materials. These are called dopants. This process is called doping. This changes the electrical behavior of the material to suit different needs in electronic devices. Now, it's important to note in metals and ceramics, impurities usually come from raw materials and are kind of accidental. But in semiconductors, these impurities are carefully selected and added only after the pure material has been refined to a very high level of purity. This level of control is what makes semiconductors so powerful and versatile in electronics like microchips and LEDs. Let's take a closer look at some of the key characteristics of semiconductors. First of all, semiconductors are materials that don't allow current to flow easily, at least not until a certain threshold is reached. Beyond that point, their resistance becomes incredibly small, almost negligible. They are typically made of elements from groups 3 to 5 on the electron periodic table. So we are talking about elements like silicon, germanium, gallium, or arsenic. Semiconductors are sort of in between. They are not as conductive as metals, and they are not full insulators either. Think of them as the bridge between these two. Now, under normal conditions, semiconductors act more like insulators, but when you apply heat, light, magnetic fields, or even voltage, something interesting happens. Some of the electrons in the valence band gain enough energy to jump into the conduction band. When that happens, the material starts to conduct electricity. But, and this is important, that conductivity is temporary. As soon as the external force is removed, the electrons return to their original state and the semiconductor goes back to being non-conductive. So semiconductors are like control gates for electricity. They stay shut until you give them the right key. Now let's talk about N-type and P-type semiconductors, the two main categories of extrinsic semiconductors. Both types start with a pure semiconductor material like silicon, but then we add a small amount of impurity to change how it behaves electrically. This process is called doping, as we discussed. In an N-type semiconductor, we add atoms that have extra electrons. These electrons become the main carriers of current. You can think of the N as standing for negative because the majority charge carriers are electrons. In contrast, P-type semiconductors are created by adding atoms that have fewer electrons. These leaves behind holes, which are basically spots where an electron could go. These holes act like positive charges, so the current is carried by the movement of these holes. So in short, N-type uses electrons and P-type uses holes, but both rely on the added impurities to do their job. And thanks to the precise control over charge carriers, we are able to build everything from diodes to transistors to integrated circuits. Let's dive into N-type semiconductors. These are created by taking a pure intrinsic semiconductor like silicon and adding an element that has more valence electrons. Take phosphorus, for example. It has 5 valence electrons, while silicon has 4. When you dope silicon with phosphorus, that extra electron doesn't fit into the regular bonding structure, so it becomes a free electron ready to carry current. These free electrons are what give the material its name, N-type, with the N standing for negative, since electrons are negative charge carriers. In this structure, the atoms we add, called dopants, give away electrons and become positively charged ions. These are known as donor ions. But the important thing is, the majority of the current in an N-type semiconductor is carried by electrons, not holes. That's what defines it. Now let's look at p-type semiconductors. These are made by doping pure semiconductor like silicon with an element that has fewer valence electrons. Boron is a common choice. Since boron has only 3 valence electrons and silicon has 4, this creates a gap, a missing electron called a hole. Holes act like positive charge carriers because they can attract and accept electrons. And in a p-type material, these holes are majority carriers. In real-world electronic devices, we often pair N-type and P-type semiconductors to create what's called a PN junction. This is the fundamental structure inside things like diodes and transistors. The junction between these two types lets us control the flow of current and generate signals. making it essential in how modern electronics works. Let's go over some commonly used semiconductors and where we see them in real-world electronics. We will start with germanium. It's an intrinsic semiconductor, which means it's used in its pure form. You will find it in diodes, transistors, and integrated circuits. Next is silicon. It's also intrinsic and one of the most widely used materials in electronics, again showing up in diodes, transistors, and integrated circuits. Selenium is another intrinsic type, mainly used in diodes. Moving on to copper oxide, which is an extrinsic semiconductor, it's doped with other elements and is also used in diodes. Then we have gallium arsenide. It's extrinsic and shows up in more specialized components like tunnel diodes, lasers, photodiodes, and LEDs. Indium phosphorus is another extrinsic material used in diodes and transistors. And finally, lead sulfate is an extrinsic semiconductor mainly used in solar cells, particularly photocells. As you can see, both intrinsic and extrinsic semiconductors have specific roles depending on the application, from power control to light sensing to signal processing. So let's wrap up this chapter with a closer look at semiconductor materials. These materials blend the properties of both metals and insulators, making them truly special in the field of material science. Research shows that the elemental composition of a semiconductor, combined with doping techniques, directly influences how well it conducts electricity. This is what gives semiconductors their versatility. Because of this, they are used everywhere from everyday computers to high speed communication systems. In fact, they form the foundation of modern technology, paving the way for continued innovation and advancement. In the next chapter, we will explore how semiconductors are manufactured and integrated into devices and how their electrical behavior is modeled and used in circuits. Germanium is a grayish-white brittle element with excellent semiconductor properties. It was one of the first materials used in early transistor development due to its high electron mobility and sensitivity to temperature. Although largely replaced by silicon in most applications, germanium is still used in high-speed electronics and infrared optics due to its superior charge carrier properties. Silicon is the most widely used semiconductor material in the world, abundant in nature and relatively easy to purify. It forms the foundation of modern electronics, including microchips, transistors, and solar cells. Its stable oxide layer makes it ideal for integrated circuits and field effect transistor FETs. Selenium is a nonmetal with photoconductive properties, meaning its conductivity increases when exposed to light. This makes it ideal for use in photocells, light meters, solar panels. While its role in modern semiconductor technology is limited, selenium was historically important in early photoelectric applications. Copper oxide is an extrinsic semiconductor material with p-type conductivity. It's often used in diodes and sensors due to its ability to absorb visible light and convert it into electrical energy. Though not as common as silicon or gallium arsenide, it finds use in thin film solar cells and gas sensors. Gallium arsenide is a compound semiconductor known for its high electron mobility and direct band gap, making it suitable for high-frequency and optoelectronic devices like lasers, LEDs, and satellite communications. It's faster than silicon in many applications but more expensive to produce. Indium phosphate is a 3-5 compound semiconductor used in high-speed and high-frequency electronics. It has a direct band gap and excellent electron velocity, making it ideal for photonic devices, including lasers and fiber optic communication systems. It's particularly valued in microwave and millimeter wave technologies. Lead sulfide is a narrow bandgap semiconductor primarily used in infrared detectors and photovoltaic cells. Known for its sensitivity to light in the infrared spectrum, it's commonly found in applications like night vision equipment and thermal imaging. Despite its toxicity, it remains valuable in specialized sensor technologies. As we wrap up our journey through the fascinating world of semiconductors, we have seen how these materials strike a delicate balance between conductors and insulators. We explored how their electrical properties can be fine-tuned through doping, giving rise to intrinsic and extrinsic types like N-type and P-type semiconductors. From powering diodes and transistors to forming the heart of integrated circuits, semiconductors play a vital role in shaping modern electronics. Their unique behavior under different conditions makes them the cornerstone of everything from smartphones to space technology. In our next chapter, we will shift shift our focus to magnetic materials, materials that respond to magnetic fields and are essential in data storage, electric motors, transformers, and beyond. We will uncover the physics behind magnetism, explore different types of magnetic behavior, and learn how materials like iron, ferrets, and rare earth alloys contribute to the function of countless devices around us. See you on next chapter.